like to see explained? Okay, so we're going to, I tried to, this worksheet that says 5-2 modeling with exponentials and logarithms, and if you're watching on the video, question first?
Yeah, on homework 34, question on 19.
You know what that is?
Yeah, so Q equals 2e to the 1 minus 3t divided by 4.
Whole thing divided by 4? Or
No, just the
3t?
3t.
Okay.
And I was confused on what, like, the rate would be.
We're trying to find the rate at which
Yeah.
this is increasing or decreasing. That's a good question. So what we want to do is we're going to have to rewrite this and use our properties of exponents. It's kind of a tricky little question here. But we want to write this as, in the form something like a equals e to the kt, where all we have is just something multiplying the t. So to separate this out, we can think of this, I'm going to think of this as like being 1 plus a negative 3/4 to the t. Are you okay with that? I'm going to kind of tease things apart here. And using our property of exponents, we know that if we had e to the m times e to the n, that's e to the m plus n. So I'm going to go right to left here. So I'm going to separate out the e to the first from the e to the negative 3/4 t. So this is now going to be e to 2e to the first times e to the negative 3/4 t. See how I've done that? So now what we really have is that, this part right here is actually the coefficient of our exponential. So this part right here, the 2e, is really our a right there. And this now, right here, is holding our e to the kt. And the rate, remember, is if you think even like, the way to remember it is like PERT. If you have this, that rate or percent growth or decrease is really the coefficient of t. And so in our case, that's going to be that negative 3/4. So that's actually our rate is that negative 3/4, which is a negative 0.75. And so then that's going to be a decrease then of, so it's decreasing by 75%. That's the rate of decrease there is 75%. But you have to really kind of unravel that, which I think is really good practice. I kind of like our book because it asks some pretty tough questions on that kind of stuff that you don't see typically. Anything else?
47.
47, do you?
On 34.
Okay, so we're still on the same place, 47.
I don't remember it though.
Do you know what that is, Nisha?
Oh, yeah. So P equals 2,500 times 1.2 to the 1/4 t. And you're finding the annual and continuous rates.
Okay. So this is in some ways similar to what we just did there. So we want to think of this as being like a b to the t power. And the b, remember, is going to hold in it whatever that percent growth or decay is. So, but we have to, before we can tell what that b is, we have to separate it out from the t. So what we're going to do is imagine that, so we know that our property of exponents, that if we had b to the m raised to the n, that's b to the m n power. So when these are being multiplied together, so we can separate those out going right to left again. You can write that as 1.2 to the 1/4 to the t power. Is that okay? And so now here, this part, we can see is going to be our b, and that's going to hold in it the r. So we're going to have to, on our calculator, go 1.2 to the 1/4 power and call that 1 plus r. And then we'll subtract the 1 and make it into a percent. That makes sense from there? So that's going to give you then the annual rate. So this is now our annual rate. And we're going to kind of do a similar thing to get the continuous rate. Because the continuous rate we're going to think of as e to the, and I like to call this case, even though we can remember it as pert, because this r is going to be slightly different than that r. And I just worry that if I call that pert, if I do this, then people can see these r's and say, oh, they're the same thing, but they're not quite the same. So it's a rate still, but I'm going to use k as that letter instead. So then you can take again this 1.2 to the 1/4 power. This time I'm going to set it equal to e to the k. And this k is our continuous rate. That's going to be our percent. So we're going to, in this case, take the natural log of both sides. And this is just going to be something you're going to enter into your calculator here. And that's going to be the natural log of e to the k, which is just k. So you'll plug this into your calculator and then make it into a percent by moving that decimal over. Okay? Tricky questions. Anything else?
25 on 33.
So this is now, we're switching to homework 33.
I don't remember which question this, but I do know that like on all of the half-life ones,
Yeah, it was.
I had a really big, yeah,
Was it
I
half-
did not get any of them.
It was the half-life.
Of something.
Yeah, I don't know. I just wrote it as an equation.
And that's fine. It doesn't
So
matter.
1/2 p equals.
So do you know what the half-life is, or is that what we're trying to find?
I can't remember what the rate was because I just wrote it down already as a.
You're trying to find the time.
Yeah.
So you're trying to find the half-life.
You don't have a
Yeah.
book?
Okay.
I don't remember what the percent is because I just wrote like 0.9594.
Well, I can find it. Do you know what
Except that
page
it's
we're on there?
Would be like 200 to 203, I think. I think that's where it was.
203 is our best guess.
Might have just been too flat. Like 200.
200. Oh yeah, Einsteinium 253 decays at 3.406% per day. Does that sound right?
Yeah.
Does that look like the decimal you're getting? So 3.406% per day. So this is how Einsteinium decays. Does that look like the decimal you get? Okay. So what we want then is, let's see what we know so far. So this is per day. So we're just going to use, our time is going to be in days. We don't have to convert this to years. And so we're going to say A is going to be however much we start with, which we don't know. And we're going to go 1 minus the 0.03406 to the t power. So there's how Einsteinium is going to decrease. Is that okay so far? And we want to know the half-life. So we want to know how long is it going to take for us to get half of what we started with. So regardless of what we started with, half of that is going to be 1/2 p. So we'll go 1/2 p. And what is that? That's going to be a 0.96599 right? And so it doesn't really matter how much we start with, because that's going to divide out. And now we're trying to solve for something that's in a variable that's in the exponent. That means we're going to take the log of both sides. Doesn't really matter which base logarithm we choose. It's not Euler's number and it's not 10, so they're equally effective. So I'm just going to use a common logarithm, and this will be whatever it is. So that will allow us to use this property of logarithms and bring that out in front. And we can go to our calculator here, but I kind of feel compelled as a math teacher to remind you that we do have properties of logarithms, and we can say that the log of 1/2 is the log of 1 minus the log of 2, because that's a property of logarithms, and also we know the log of 1 is 0, and so this is really the negative log of 2 is t, and then we'll just divide this over the log of 0.96594, and then you go to your calculator there. Now you don't have to do this, because you can just take the log of 1/2 divided by the log of that, but I try to never miss an opportunity to reinforce properties of logarithms. Other questions? Okay, so let's take a look at that notes worksheet, and if you're watching the video, you can pull that up on Canvas as well, and we'll try to work through that a little bit. The hardest questions are at the end, so I just want to watch my time. I think we're okay, but I want to make sure we do the last couple of those and don't run out of time and not get a chance to do those. But we've talked about these kind of problems a little bit before. So if we have city A has a population of 50,000, so city A has a population of 50,000, and it is growing by 3.5% per year, and city B starts with a population of 250,000, and it increases by 1.6% per year. When are they going to have the same population? Have we done the same problem in here? Let's change it then. So let's change it. So you remember how to do it? So let's change it and say that A has a population of 25,000 rather, and it's growing by, we'll say 7.2% per year. And we'll say city B has a population of 100,000, and it's, let's make it more interesting, say it's decreasing by, we'll say 1.9% per year. Okay, so smaller population is increasing, bigger population is decreasing. So one's going to be exponential growth, one's going to be growing, and the other one's going to be decreasing. And we want to find out when do they have the same population. And you know how to do that? So you're going to set them equal to each other. Oh, let's get the equations, I guess we should say. That's kind of the more interesting of the questions. So A of t, that's the population of city A at time t, is going to be what?
300,000 times 1.072 to the t.
Okay. And we're going to set that equal to B of t, which is
100,000. 0.9.
It's actually point. So it's going to be 1 minus 0.019. See how to subtract by adding? Have we done that? So you know that you're going to carry 1 at the end, so you want these to add up to be 9 and the last one to be 10. So that's going to be 981. Trick to do elementary school math, right? Or middle school math. And we're going to set those equal to each other. The tricky part's going to be, how do you set your window? So, you know, the biggest one has 100,000.
We'll divide by
To start.
25,000.
Oh, should we? Yeah, we can do this one without. Should we do this one? Maybe more interesting. We can solve this one without using our graphing part of the calculator. That's more fun anyway. So we'll take the 25,000 times 1.072 to the t equals 100,000 times 0.981 to the t. So without graphing this, then what should we do?
Divide by 25.
Okay, good call. We'll divide by the 25,000. You just as soon avoid, I mean, you can divide by the 100,000, but we'll try to avoid the fractions. What else are we gonna do?
I take the log of both
Oh,
sides.
whoa, not yet, hold on, we're not ready for the log yet.
Divide by 0.981,
Yeah, so divide by that,
and then we can factor out the t.
there you go. So the interesting part here, if you have each of these raised to the t, you can write it as the fraction 1.072 over 0.981 to the t power. This is the interesting math part of this. And then 100 divided by 25 is 4. Is that okay? And now we can take our log on both sides. And use our property of logarithms to make that t into a multiplication. And do that division of two logarithms. And this can all go in as one calculator entry. That's what I'd recommend. I think you're less likely to make an error and easier to troubleshoot if you get the wrong answer to see where you might have entered something in wrong if you just do it as one entry. Do you need a calculator, Jesse? There's some rentals available there if you want. I'll pull my calculator here as well. So log of 4 divided by the log of 1.072 divided by, oops, didn't do that right, divided by 0.981, close the logarithm, getting 15.627 years. Agree. Okay. All right, so let's jump down to the doubling time or triple. We did this one too.
Yeah, we're on the
Should we jump down to half-life? Those are more challenging anyway. So we'll jump down to carbon 14. Decays at an annual rate of 0.0121%. So C14 decays at 0.0121%. Show the half-life. We did this one too, didn't we?
No.
Can we do this one in here? Okay. Half-lives are always tough. So anybody know how to get started?
We could write an equation.
Let's write an equation. I think that's a great place to start. So
I should be what, 130.5 T
One
equals.
minus,
hold on. Let's just get the equation first, then we'll do the half-life thing.
1 minus 0.0, no, yeah, wait. This is already in a percent, that's like,
So we need it as a decimal.
yeah, that's a lot of zeros.
That's a lot of zeros. How many zeros exactly?
0,
0.000121.
This is going to decay slowly, right? Its half-life is going to be 5,000 some years.
and then k to the 11, or k times 11.
10 times 11.
Where the hell is, no,
Oh,
sorry,
half-life
excuse me,
of-
where's the 11 come from?
You're doing the problem above that. Oh, I didn't realize they were different.
Yeah, let's do the same problem here.
And I was like, and I go,
Okay.
Where's the 11 from the second?
Yeah, that's going to be the next one.
lot of units.
Oh, okay. Wait, because half-life is like if you have an amount of substance, how long until there's half of that substance?
So half of it decays, yeah.
Okay, I never heard that.
So some things, like some of these radioactive things decay really slowly. Like we're gonna see here, it's gonna take thousands of years for half of it to decay.
They
Others are
actually
really-
say carbon 14 for like carbon dating for like fossils.
That's exactly right.
Yeah, and so they use like the total amount of like carbon and they find like how much is left of it, and then they use carbon dating and like the rate at which carbon 14 decays to find it like how old it actually is. That's true.
Does that make sense? So you find some old fossil of something, and you know what the living thing of that, how much carbon it has in it, carbon 14 it has in there, and you compare how much carbon 14 is with the fossilized sample and say, oh, you know, how many thousands of years old is it?
How do they know how much was in the living thing?
Because you can test the living thing. Like,
What if it's like
Well, you
extinct?
could see what it decays into. You could, like carbon 14 probably decays into like carbon 12 or like some other element. And so you could take that out of the total, so you can see how much carbon 14 compared to what it decays into, and then just take that as a percentage.
That went right over my head, but let's carry on.
Okay, so we're gonna say half P is P times, what is this gonna be, 0.99987 to the T, subtracting by adding, does that make sense? And the P's don't matter, and then we can take the log of both sides, and who could resist using our properties of logarithms, and making that into that equation. You with me on that?
Yeah, and then we ended up with 5,000. Yep, that's right.
Pretty close to whatever they said it was gonna be.
5,728. Yeah.
And once you get that to 3 decimal places, 5,700.
28.143.
Which is pretty close to 5,728 years. Is that okay? You all right with that? Okay, so now the next one's a really hard one, I think. So if we have Q is equal to that, the half, no, that's not the hard one yet. That's down later on the page. So Q is now we're going to do it exponential. So the idea is you can do half-lives using annual rates of decay, but you can do it just as easily with, or just as difficult, using exponentials-based Euler's number. So essentially anything you do with one, you can do with the other. So we have Q is Q sub 0 e to the kt. So Q of t is Q sub 0 e to the kt. And half-life is 11 minutes. And we want to solve for K. So remember the K is our growth rate. So since this is decaying, would we expect K to be positive or negative?
Negative.
Good. So, and we're going to say, how much do we have to start with at time 0?
1.
0. Wait, or not. Whoa, no.
We put in 0 for T,
We just have to
Q sub 0. Yeah, so this is like the P that we were using in the other equation. Q sub 0 is the amount we have at time 0. We don't know what it is, but it doesn't really matter. So if we have half of that, then how much are we going to put where the Q of T is?
0.5 uses that.
Right. So it doesn't really matter what the Q sub 0 is, it's going to divide out. And then we're going to put the 11 in where the T is. And that's going to allow us to solve for K, which we're going to write as a growth rate, as a percentage decaying. Is that okay? So the only real difference here after we divide out the Q sub 0 is which logarithm do we want to use? Yeah, natural log because of that exponential base Euler's number. So still we get to use our properties of logarithms, which is always fun. So we could say the natural log of a half is natural log 1 minus natural log 2. The natural log of 1 is also 0, making this a negative natural log 2. And then when we take the natural log of e to the 11k, that's going to be just the 11k. So we get to say k is going to be the negative natural log 2 over 11. Follow all that? Bless you. Okay, and then it goes to your calculator. And so first give me the decimal before we make it a percent. What is that?
-0.06301.
And then we'll convert that to a percent and say it's decaying at,
6.301%. Negative.
so either it's a negative 6.301% growth rate or it's decaying at 6.301% per year continuously. Okey doke. All right. So we are going to do,
Hard one.
not yet. Kyle's down
The
there.
21% one.
Yeah, that's the one where it's going to be tough. So let's convert Q equals AB to the T and from annual percent to a continuous. These are always a bit of a challenge. So we are saying that B is, okay, we know that. So P is 175 times 1.145 to the T power. And we want to convert that to something that's based Euler's number. That make sense? Should we do it at the board or do you want to just stay parked? Oh, there we go. I'll pause the video for a moment. So we have agreed that the initial value for both of these is the same. And we're going to equate the base of this exponential, the 1.145, with the base of this exponential, which is the e to the k. And we can solve that by taking the natural log of both sides and recognizing that a logarithm base Euler's number and an exponential base Euler's number are inverses. And so we'll get k is equal to whatever that was. What was it as a decimal?
1.13540.
Or
Sorry, no, 0.135.
0.13510. 13540. And then making that into our percent. So it's going to be 13.540%. So we can see that this is a 14.5% annual rate of increase, and because of all the compounding we get with Euler's number, that's continuous. So an infinite number of compounding, we just need 13.540% growth. Is that okay? All right, very good. So let's try going the other way, and can we convert an exponential based Euler's number to an annual rate? So I guess we were just going to write it here. So we would have said this is, the question I guess that was asked was how to write this as the equivalent continuous rate equation. So this equation is the same as that original one there. Okay. Let's bring the other group to the board, and we'll solve Q is equal to 7e to the, let's just do 3t, is that right? Or is that, and we're going to convert that to Q equals AB to the T. So again, if you put in 0 for the t, you can find that little a pretty straightforward. And then you're going to, so hopefully if we plug in 0, you can see that our little a is 7. And then we're going to see that these bases are going to be equal to each other. Was that a point? Is it a 0.3?
I used point.
I used 3.
Yeah.
Oh.
3 is going to be pretty big, right?
Yeah, it is. Not
Should
really.
we go with 0.3?
Erin, that's huge. 2,000%. I can't read your writing, but that looks like 2,000%.
It's like 19,000%.
Okay then. That was a pretty overwhelming response.
So we decided to call that a 0.3. Are we getting 1.350?
Yeah.
There we go. Happiness.
So we will write this as Q equals the 7 and then 1.350 to the t power. Is that okay? Okay. You okay with that, Emily? Yeah, how do you want to check in on Emily there real quick?
I just don't think it has to equal 1 plus R. I think it just equals K. So what I know is or not B. It equals 1 plus. I mean, it does.
It does?
It has B because.
Since when?
Yeah, so B is just the e to the 0.3.
Yeah. Oh, we're solving for B. Okay, my bad. Oh, yeah. I mean, you get the same answer.
Yeah, you can get the R, but then you're just going to go right back to writing B as 1 plus R. Yeah, I think we're okay. Okay, let's do the one I wanted to make sure to talk about is that if you go to the 21% radioactive decay in 8 hours, and then let's find the half-life. Let me do that one with you here, just to make sure, because it's really 2 problems in one. So 21% decays in 8 hours, and we want to find the half-life of that substance. So we're going to first solve this and find out what the rate is, the annual rate, or you could do continuous rate, it doesn't really matter. Then we're going to turn back around and do a second problem where we're going to find the half-life.
Can we do it in hours? Do we have to do it?
Yeah, I would leave it in
Okay.
hours. Yeah, I would say we'll just use whatever time they give us. So our time is going to be measured in hours. So if it decays, if 21% decays, how much do we still have?
79%.
79%. So we'll write that as 0.79 P is going to be the unknown amount we start with P times we don't know what that rate of decay is. That's what we're going to try to find the first time around. The time that it takes for 21% to decay is 8. So we're going to first solve this for R, and then we're going to come back and do another problem to get the half-life. So it's really kind of a hit it in 2 problems in one. So we can divide that P out. And then to solve for the R, we're going to raise it to the 1/8 power. And I wouldn't, I would just get that decimal if you want, or you can leave it as 0.79 to the 1/8. But I don't think you want to subtract 1 and then make the R percent, because we're going to need this same base in a moment. So somebody just tell me what they've got for like 3 decimal places. 971. So we're not going to use the rounded number, but it gives me something to write down. Okay, so that's the 1 plus R of the base. Now we're going to come back and find the half-life. So now doing the half-life, we're going to say we want half as much as what we started with. Our 1 plus R, we have said, is 0.971, and we need to solve for the T, where the T is how many hours it's going to be until we only have half of what we started with. That make sense? So we can divide out that P. And now we're in hopefully kind of familiar territory. Oh, just love using these properties with logarithms. I know you do too.
It's the one thing that breaks me drawing.
Yes. So I think we're gonna get that time. Now don't use your rounded 0.971. So you need to go back and capture all the decimal places on your calculator. And did you get that already, Nisha? What is that?
23.524 hours.
That's gonna be in hours, good. You getting confirmation? Did you get that as well?
Mhm.
Nice. Okay, so the tricky part is it's really a 2-for-1. You get 2 pretty involved problems just to get the one answer that you were asked to find. Okay, let's do, see if you can do, now the last one is the other one. So this is the one where you have an exponential 2 times 1.02t's. 2 times 1.02 to the t. And we want to know when is that equal to a linear 4 plus 0.5t. So unlike that one before where we could divide the exponentials and convert them into a single exponential, there's no way to do that with this problem. So I don't know of another way you can do this except to graph one side as y1 and the other side as y2, and then find that point of intersection. And this is where you may have to play around a bit with your window. Remember, in this case, I don't think it makes sense to get the negative answer. There's going to be 2 points of intersection. But in the context of this problem where you're talking about population growth and food supply, I don't think a negative value of t is going to make any sense. So I would just go pursue that one that's to the right of the y-axis. Anybody have it? You have to play around with the window a little bit. No?
I only have the negative one.
Oh.
My calculator,
Yeah, the windows.
Yeah, that's why I don't like that strategy as much. It can be kind of time consuming if you've got this in front of you.